Essentially, all of today's chemicals and materials, from fuels to plastic bottles to vitamins, are made from the oil that we dig out of the ground. This constitutes our quality of life. Unfortunately, the use of this oil has led to an increase in energy demands, higher prices, and climate change. The balance between our quality of life and the industry standard of using oil has motivated a growing need for greener and more sustainable methods to produce fuels, medicines, and specialty chemicals. I'm Ashty KARIM, a chemical engineer developing a major shift in the way that we address these problems, going beyond the traditional use of chemistry or biology alone. Now, let me give you a brief example. Let's talk about plastics. They're everywhere, right? I mean, Tupperware, plastic bags, bottles of any shape and size. How many of you have drank out of a plastic water bottle today or within the past week? Okay, a good number of you. Now, how many of you actually know how that plastic bottle was made? Very few of you, okay? Let's talk about the chemistry of how plastic bottles are made. Typically, plastic pellets made from oil are melted and sent through an extruder like this one here. As it passes through the extruder, these plastic pellets are then transformed into plastic preforms. They look like these. The plastic preforms are then pressurized and cooled in molds to get the shapes that we buy from the stores. These manufacturing processes churn out about 10,000 plastic bottles within 1 hour. That's pretty spectacular. And unless you live in a remote location, you're probably swimming in plastic. The fact is, 26 million tons of plastic bottles are made per year in the United States. That's the weight of 100,000 passenger airplanes or 500 Titanics. It takes 200 million barrels of oil to make plastics in the US per year. But we recycle, right? That accounts for 6%. So we're left with 190 million barrels of oil to make just plastics in the US per year. I don't see us making any less plastic in the near future. So if there were only a way that we could reduce the amount of oil that we use to make plastics, instead of thinking chemistry, why not biology? Can anyone tell me what the difference is between these two water bottles? Anybody? Yeah. Yeah, the one on the right has a green lid. The one on the right is actually made out of bioplastics. So instead of using oil to do chemistry to make plastic bottles, we can use sugar to do biology to make plastic bottles. In this case, the plastic pellets that we talked about are made from plants that can make the same chemical that plastics are made of. This is one example of how we can use biology to address a key societal issue. But it's not the only example. Many engineers have learned to use bacteria and even baker's yeast to do some of these things. Now, normally you'd think bacteria are bad. And while there are bad bacteria that cause disease, there are also good bacteria, like the bacteria in your gut that help you digest food. Scientists have been able to manipulate good bacteria to make products from simple renewable starting blocks for centuries now. Some of the oldest examples include the use of yeast in the fermentation and leavening of food and alcohol. So the yeast have all the right parts to make these delicious edibles. Effectively, bacteria and yeast can be treated as miniature chemical factories to produce these products. If we've been doing this for so many years, why is it still difficult? Why is it so expensive, and why is it time-consuming? In order to demonstrate this to you, I need 2 volunteers. 2 volunteers. Anybody? Okay, you here, and then you there. Awesome. Yeah, come on up, come on up. Okay, one of you stand over here, and the other, you can come over here. Sweet. Okay, so what's your name?
Kayla.
Kayla? Nice to meet you. And what's your name?
Sarah.
Sarah, very nice to meet you. So Kayla and Sarah are my bacteria, okay? And so I'm going to tell my bacteria different instructions, and so you're going to do that, okay? And so the first thing is face the audience. Okay, now take your left hand and rub your stomach. Okay, whatever I tell you to do, keep rubbing your stomach, okay? My bacteria are happy, they're growing, okay? Not a care in the world. Now, I'm the engineer, and I want to manipulate my bacteria to make something that I find useful. So I'm going to ask them to make a couple of steps and do different things so they can make my product. So, still rubbing your belly, take your right hand and pat your head. Okay, pretty easy. That's the first step in making the product I want them to make. Okay, now bend your left knee and pick up your left leg. Okay, now swing your left leg. Okay, now tilt side to side. Now smile, now laugh. Now pick up the paper in front of you. Okay, thank you. Give Kayla and Sarah a round of applause. You can leave them there, thank you. So it wasn't very easy. And as an engineer, it's not very easy to manipulate bacteria to make something that I find useful. Because the fact is, they want to grow, and they want to be stable while doing it. Developing and engineering bacteria is expensive and time-consuming. There's a tug of war between bacteria wanting to grow and us wanting them to make a product. And while we've gotten good at harnessing biology, we still can't make enough product, and the products that we can make are limited. My research involves cell-free systems in which we cut open bacteria, remove the walls of that miniature chemical factory, providing direct access to the machinery within. It's like breaking an egg. When you remove the shell, you have access to the parts that you want. With greater control over the bacterial parts, we can conduct precise chemical synthesis without the use of intact bacteria. By merging biology and chemistry, we can now develop even better plastics. We can find alternative fuels, or even discover new medicines. We can prototype or test out bacterial parts together in new ways from one or multiple bacteria. We can even test out parts from scratch. We can test out all possible combinations in a fraction of the time that it would take with live bacteria. These reactions take only a few hours and takes minutes to set up. This is in comparison to years of laborious effort to engineer bacteria when they're alive. I've even found a way to couple this cell-free framework with robots. Well, not these robots, liquid handling robots. These robots take liquids from one location and move them to another location. So if I supply them with the bacterial parts, they can set up the reactions for me. I can now rapidly screen cell-free combinations and discover new information about biological systems that was previously confounded in living organisms. With the increase in speed and the removal of the bacterial constraints, we can now rapidly use cell-free systems to make better fuels, to create stronger materials with new beneficial properties, or even to discover new antibiotics that we're so desperately in need of. Characterizing and engineering biology in the cell-free environment provides an efficient way to design, build, and test systems to create new chemicals. You could even imagine making chemicals that were impossible by chemistry or biology alone. It's a little crazy, but I even envision a world where all of our material items are made from biology. Wouldn't that be something? Cell-free systems could pave the way to make the products we buy greener, better, and cheaper. Thank you.